The electronic configuration of an atom is the representation of the arrangement of the electrons that are distributed among the orbital shells and subshells. So we use electron configurations to describe the orbitals of an atom in its ground state, but it can also be used to represent an atom that has been ionized, so either into a cation or an anion, by compensating with either the loss or the gain of electrons in the subsequent orbitals. Many of the physical and chemical properties of elements can be correlated to their unique electron configuration. So the most important aspect of this is to look at the valence electrons. So these are the electrons on the outermost shell, and these are extremely important because they determine the unique chemistry of each element. So electrons exhibit a negative charge and are found around the nucleus. So electron orbitals are the position of the electrons around the nucleus and is determined as the volume of space in which the electron can be found within 95% probability. So there are 4 different types of orbitals: S, P, D, and F, and they all have different shapes, but one orbital can hold only 2 electrons. So the maximum for an orbital is 2 electrons. So P, D, and F orbitals have different sublevels, unlike the S orbital. Therefore, they can hold more electrons. So let's look, for example, at hydrogen. Hydrogen has 1 electron. Therefore, the 1 electron, we find the 1 electron in the 1s region. So 95% of the time we can be certain that it will be there. So 1 represents the orbital in the energy level, which is closest to the nucleus, and S represents the shape of the orbital. So this, for example, up here, this is what an S orbital looks like, where in the middle, in blue, we have the nucleus, and the dots represent sort of the different positions at different times of where the electron can be found. So by creating this sort of spherical probability, we can then imagine where it might be at a particular moment in time. There is also a 2s orbital, which is shown here. So again, we have the nucleus. This first sort of circle is the 1s, and the 2s is further out. So again, 2 will represent how far those electrons are from the nucleus. So 1 is the closest, and 2, 3, and 4, and so forth is when we move away from the nucleus. And S stands for representing the shape of the orbital. So we can see that the S orbital is spherical in shape. The other orbital is the P orbital. They are shown here. They look like dumbbell shape, or you can also think of it as 2 balloons tied together and sort of held in the middle. Unlike the S orbital, the P orbital has a direction. So we can see here the different axes. So we have the Y axis, the X, which is the horizontal, and the Z, which is sort of, if we look at it in 3D, it's sort of coming out from the computer screen and going back into the screen. So it has a particular direction. And this is the second energy level after the S orbital. So sometimes you can assign you can give it the axis name, so it can be Px, Pz, and Py, and each one of these will hold 2 electrons, or you can just say 2p6. So 2 represents the fact that it's the next one after the first orbital. P is saying that is what shape it is, and 6 is representing the number of electrons. But in general, you don't have to specify that Px2, Pz2, Py2. It's just easier to put it as 2p6. And then after P, we have a 3rd level, which is known as D, and the D orbital, and it has 5 sublevels. And the 4th level is F, which has 7. these electron configurations matter? Well, because, as I already mentioned, they determine the valence electrons of an atom, and that's what makes each atom unique. And therefore, by knowing the how many electrons are in the most outer shell, we then can kind of look and examine the different chemical reactions it undergoes and why. So, when we represent these, there are different ways. So, I'll be looking at electrons in boxes, also SPDF notation, and noble gas notation. Just a quick overview. So, as I mentioned, we have S, P, D, and F, which is the name of the subshell. The S subshell has only one orbital, therefore it can only have 2 electrons. P has 3 orbitals, the px, y, and z. So since each orbital can carry 2 electrons, we multiply that by 2 and we get 6. For D, there are 5 orbitals, therefore it can carry 10 electrons, and F, there are 7 orbitals, so we multiply that by 2 and we get 14. So let's first look at electrons in boxes. So it's quite simple once you get the hang of it, but so one box represents 1 orbital, therefore you can put 2 electrons in a box. We represent these by arrows, either up or down, which shows the spin of the electron. So, and when you have 2 electrons in a box, the spin has to be pointing in opposite directions to show that each electron has an opposite spin, which is known as the Pauli exclusion principle, and I'll show you what the boxes look like. So this is what the electron box notation would look like. As you can see, the arrows show the spin of the electron, so you can't have them pointing in the same direction because that would be wrong. So another thing to know about this is how do we actually fill them. So there are 2 sort of useful diagrams to look at. So we fill them in terms of energy level. So as from this top diagram, we can see the, on this axis that the energy is going up. So we start with the lowest energy, which is closest to the nucleus, which is 1s. We go to the 2s, then to the 2p, 3s, 3p, 3d. There is an exclusion here. We have to put the 4s before the 3d because it has a lower energy. And for the exam, if you have to write out, let's say you're asked to write, I don't know, any element like, I don't know, bromine, this would be a useful way to sort of remind yourself of how to fill the boxes. In this case, the increasing energy is going down, so we start with 1s, that we then fill the 2s, we then go to 2p, 3s, and we go 3p, 4s, 3d. So this is the one where it sort of helps you to remember that you have to fill in the 4s before the 3d. So let's actually look at an example here. So we have nitrogen, and nitrogen has 7 electrons. So when we're filling in these boxes, before we can fill sort of the next level, so before we can fill the 2p, we have to make sure that the 2s and the 1s are fully filled. So we start off with 1 electron upwards, 1 downwards. Then we go to the 2s level, 1 upwards, 1 downwards. And another thing that when we're filling these boxes, we need to an electron will occupy a box singly first before pairing, and this is the known as Hund's rule. So if you think about it, like when you get on the bus and there is a lot of seats available, people prefer to sit individually, but as more and more people get on and all the sort of people that were sitting alone, there's no more space, so people have to join and sit next to each other. So that's sort of the same principle. So the 2p, as we know, has the 2px, 2py, and 2pz. So think of it as 3 seats. So as one person gets on, sits there, another one sits there, another one sits there. We can see the same for oxygen, which has 8. So once we filled up all these single boxes alone, we can then add the 8th electron with the opposite spin to the empty box. So let's look at the electron SPDF notation. This is the more common way of doing it, because you don't have to draw boxes out. The way it's done is it's written as, let's say, 1s2 or 2p6, 3d4. So we can see here 1 represents the energy level, S represents the type of orbital, and the 2 represents the number of the electrons. So again, this is sort of the order of filling them, and as I said, we need to fill the 4s before the 3d because it's at a lower energy level. And I also thought it would be quite interesting for us to do an example. So let's look at yttrium, which is Y on the periodic table. It has 39 electrons. Let's also briefly look at noble gas notation, which is another way of simplifying it. So as the p subshells are filled, it reaches the group commonly known as the noble gases, and the noble gases have the most stable electron configuration because all their subshells are filled, and that's what makes them inert. So we can conclude from this that all noble gases have their subshells filled, and we can use them as a shorthand way of writing electron configurations for subsequent atoms. So let's look at vanadium as an example. So here I've got a periodic table, and vanadium is found here. It has 23 electrons. It is in the 4th period, so 1, 2, 3, 4, in the 4th period, and the 5th group, so 1, 2, 3, 4, 5. The noble gas that is before it, so the noble gases are here. So if you look at the previous, so argon with 18 electrons is the noble gas before it, so we can use that as our reference. So now we need to find how many valence electrons there are. So we just do that by simply minusing 23, which is the number of electrons of vanadium, minus 18, which is the electrons for argon, and we get 5. So instead of having 23 electrons to distribute in orbitals, we now only have 5, which gives us enough information to build. So we simply start at a new 4s subshell. So this is what it would look like. So we would put argon in square brackets as our reference point, and then we would add the 5 electrons, 4s2, 3d3. So this video I've covered in terms of the specification. We looked at 1.5 F, G, H, and I, just for yourself, so you can be sure. So make sure you practice writing electron configurations for the first 36 elements, so from hydrogens to krypton. So this includes the 1s notation and electron in boxes. So you can use the sort of noble gas to make it slightly easier for yourself. So I thought we could do some practice questions. If it might be useful for you to pause this video and see if you can answer them, and I will go through them briefly. So let's look at question 1. It says find the electron configuration of the following. So the first one is silicon. So if you look at the periodic table, we can see that silicon has 14 electrons, and the noble gas that is in front of it is neon, so we can use that as our reference point. So we put Ne in square brackets, and we know that neon is fully filled, so we minus 14 minus 10, so 14 is the number of electrons for silicon, and 10 is the number of electrons for neon, so we have only 4 electrons to distribute. And since silicon is in the in the p, we know that p will be the last, so then we do 3s2, 3p2. For tin, we use krypton as our reference point, and we need to fill in 14 electrons, which is in the fifth, so it's 5s2, 4d10, sorry that was meant to be short, and 5p2. For lead, that's a more complicated one, we use xenon as our reference, and then we have 6s2, 4f14, 5d10, and 6p2. We wouldn't be asked to do that because that's too long and too complicated. So it's a good question too. It says, so we are given a scenario. You're currently studying the element iodine and wish to use its electron distributions to aid you in your work. So A, find the electron configuration for iodine. So we look at the periodic table, we can see iodine has 53 electrons, and the noble gas before it is krypton, so we use krypton as our reference point again. Mine is saying 53, sorry, so we do 53 minus 36, which means we have 17 electrons to distribute, so it's 5s2, 4d10, and 5p5. Part B is asking us how many unpaired electrons does iodine have? So to find the answer, we refer to part A, and look at the valence electrons. We see that iodine has 5 electrons in the p orbital, which is here. We know that the full p orbitals will add up to 6. So using Hund's rule and Pauli exclusion principle, we can make a diagram to show the 5 p orbitals. So we draw 3 boxes, and there is px, py, and pz. So we start to fill them up, first singly, and then we add them. Remember to do the opposite spin. So we can see that there is 1 valence electron, meaning that it's unpaired. So let's look at question 3. So in your own words, describe how to make an electron configuration and why it's an important skill to have in the study of chemistry. So the first part is quite straightforward. So the important aspect is, by knowing the electron configuration, it will help us to determine the valence electrons of an atom. And this is important because valence electrons contribute to the unique chemistry of each atom. The second, we describe the major concepts and explain why they are a key part of our toolkit when describing electron configurations. So we know that the main tools we have in writing electron configurations are orbital occupation, Pauli exclusion principle, Hund's rule, and the Aufbau process. So orbitals are occupied in a specific order, thus we have to follow this order when assigning electrons. Pauli's exclusion principle states that no 2 electrons can have all 4 quantum numbers the same. The 4th quantum number that refers to spin will denote one of 2 spin directions. That means that one orbital, there can only be 2 electrons and they must have opposite spins. This is important when describing an electron configuration in terms of the orbital diagram. Hund's rule states that electrons first occupy the similar energy orbitals that are empty before occupying those that are half full. This is especially helpful when determining unpaired electrons. And the Aufbau process denotes the method of building up each subshell before moving on to the next. We first fill the 2s orbital before moving to the 2p orbital. Question 3c. Why are we able to abbreviate electron configurations with a noble gas in the noble gas notation? So we know that a noble gas has all of its orbitals filled, so it can be used as a shorthand or abbreviated method of writing all of the electron configurations after 1s. And 4, we have to identify the following elements. So the first one, so if we count all the numbers which are up here, so 2 plus 2, 4, 10, 12, 18, 20, 26. So then we look at the periodic table. What has 26 electrons? It's iron, so this is Fe. We do the same for B. When they all add up, it comes to 45, which is the element Rh, which is in the transition metals. We look at C. It adds up to 16, which is sulfur. And the last one adds up to the element called polonium, which is Po on the periodic table. Yeah, Po. So there we go. Thank you for listening.